Hi, welcome to the video. Today I'll talk about our result sample and gather fast ruling set algorithms in the low memory MPC model. This is joint work with Kishore Kottapalli from IIIT Hyderabad and Sriram Pemaraju from the University of Iowa. I am Shreyas Pai. A full version of the paper is available on arXiv. The link is at the bottom of the screen. Consider the maximal independent set problem, also called MIS. We are given an n-vertex graph, G, with m edges and maximum degree delta. We want to find an independent set I such that every node is within one hop of some node in I. Here is an example of a graph with the orange vertices forming a maximal independent set. Note that these vertices do not have an edge between them, therefore they are an independent set, and every other vertex, that is the blue vertices, are within one hop of some orange vertex. Notice that the blue vertices also form a maximal independent set for the same reasons. So this also signifies that we are not looking for any particular maximal independent set. Any maximal independent set will suffice. We can generalize the definition to beta ruling sets. A beta ruling set is an independent set I such that every node is within beta hops of some node in I. And this definition is for an integer beta greater than or equal to 1. Notice that an MIS is a 1 ruling set, and it is also a beta ruling set for any beta greater than or equal to 1. This tells us that for beta equals 2, the two maximal independent sets in the previous example are valid beta ruling sets, two ruling sets, but also notice that this single orange vertex also forms a valid two ruling set because every grayed out vertex is within two hops of this single vertex. In this paper, we consider the massively parallel computation or MPC model. This model is a theoretical abstraction of modern parallel and distributed systems like MapReduce, Spark, Pregel, etc., and it was introduced in Karloff et al. In SODA 2010. A main attraction of this model is that it allows all-to-all communication between the machines. In the MPC model, we have a set of machines having local memory of S words each. The machines get an input of total size capital N. When the input is a graph, capital N is the number of edges m plus the number of vertices n. The local memory per machine is assumed to be much smaller than the input size. In particular, S is assumed to be strongly sublinear in capital N, which is the input size, which is that is n to the 1 minus delta for some constant delta between 0 and 1. This is a very crucial assumption that makes the model very practical. In the MPC model, we have machines at round t. They receive messages from the machines in round t minus 1. They perform some local computation and send messages to machines which they will use in round t plus 1. The main restriction in the MPC model is that the number of messages received and sent by a single machine is restricted to be the local memory parameter of the machine. That is, the number of messages received at any round at a particular machine is restricted to be S words, and the number of messages that it can send in any round is restricted to be S words for every machine. Notice that a single machine can send all of its S words to another single machine, provided that all of these local constraints at each machine are satisfied in each round. For graphs, there are different regimes. Notice that for graphs, n, which is the total input size, is the number of edges plus the number of vertices, and S, which is the local memory parameter, is strictly sublinear in the total size of the graph. But if we try to relate S and the number of vertices, it leads to three different regimes. The first is the superlinear regime, where S is n to the 1 plus epsilon for some constant epsilon. This regime only makes sense for dense graphs. Then there is the near linear regime where S is roughly order n. And then there is the sublinear regime where S is O of n to the epsilon for some constant epsilon between 0 and 1. This sublinear memory regime is the one that we will concentrate on in this paper. The sublinear memory regime is also called the low-memory MPC model. In the low-memory MPC model, simulating classic PRAM and CONGEST algorithms gives us O of logn round algorithms for MIS, maximal matching, and connectivity. For connectivity, it is conjectured that theta logn is the correct round complexity, but we don't know any good lower bounds. In fact, the only lower bounds that we know are of the form omega 1 over epsilon, and since epsilon is assumed to be a constant, this is a constant round lower bound. For MIS in the low-memory MPC model, in general, going below log n rounds is very challenging, but perhaps surprisingly, for MIS and maximal matching, we have O tilde square root log delta round algorithms that break this logarithmic barrier. So a question that arises is, can we get a better running time for two ruling sets? In the low-memory MPC model, using the simulations by Karloff et al., we can get logarithmic round algorithms for connectivity, MIS, and two ruling sets as well. Using the Ghaffari and Wito algorithm, the complexity of MIS is square root of log delta. And since an MIS is a valid two ruling set, this bound applies for two ruling sets as well. And in this work, we show that two ruling sets can be computed in log delta raised to 1 over 6 rounds. We present sample and gather simulation theorems, and using these we show how to compute two ruling sets in log delta raised to 1 over 6 rounds, and more generally we show how to compute beta ruling sets for beta greater than or equal to 2 in log delta raised to c rounds, where c decreases exponentially with respect to beta. Sub-logarithmic algorithms in the low-memory MPC model, like the ones in Ghaffari and Wito, work by trying to quickly simulate an R-round congest algorithm where R is log or O of log delta. From O of log delta congest rounds, we get to O of square root log delta MPC rounds through this quick simulation. Let me define the congest model first. The CONGEST model is a synchronous message passing model where we are given a graph, which is the communication network, and the nodes can send log n bit messages per neighbor per round. Notice that in the main difference between the MPC and the CONGEST model is in the communication network, where in the CONGEST model, the input graph is the same as the communication network, and in the MPC model, we are given an input graph, but the communication network is an all-to-all communication network. A round in the CONGEST model looks as follows. A vertex receives messages from its neighbors, performs some local computation, and sends messages to its neighbors. And all of these messages are restricted to be O of log n bits each. So if we want to simulate L congest rounds in MPC, we need to gather the ball of radius L of L hops around the vertex that we are interested in simulating. This ball can be of size delta to the L and can be collected in O of L MPC rounds by basically collecting an I hop ball in I rounds, just by going one hop at a time. But one can do a lot better in the MPC model by exploiting the all-to-all communication. Notice that, let's say we have computed an I-hop ball around the orange node, and also that in parallel we have computed I-hop balls around each node in this neighborhood. Then if we get all of these IHOP balls in the IHOP ball around the orange node, we can compute the 2 hop ball around the orange node. This allows us to compute the delta to the L-sized L-hop ball in log L MPC rounds by iteratively doubling the size of the ball. Now notice, you may have noticed that these balls may not in fact fit in a single machine. So the way we handle this is by looking at sampling. So let's say we are given somehow given an information that these two vertices on the left are not going to participate in the L rounds. Then we can simply ignore them when we are growing the ball around the orange vertex and only grow the balls on the active vertices. So then we get a much smaller ball of radius L, and we can also again collect it in log L MPC rounds. And notice that since this ball is much smaller than the actual ball of radius L around the orange vertex, we can actually uh, gather a larger ball around the orange vertex since it will fit into memory, uh, since it can fit into memory. So that will allow us to simulate more rounds at a time. So this leads to our sample and gather simulation theorems, where we observe that many such congest algorithms involve rounds where only a sampled set of nodes is active. If we can estimate these sampling probabilities quickly, then we can use them to subsample a ball of radius L so that it fits into memory. This leads us to get sample and gather simulation theorems in which an R-round congest algorithm is simulated in R over square root log n base alpha rounds of MPC model. Here alpha controls the sampling probability, and I will give some intuition as to what alpha looks like later on. So pictorially, we have an R congest round algorithm. We take a chunk of square root log n base alpha rounds. This will be our L. We will apply our sample and gather simulation theorem, and it will give us a way to simulate these square root log n base alpha rounds in roughly log n MPC rounds. And that gives us the final running time. Some previous work. Our simulation theorems are in fact inspired by a similar simulation theorem due to Benezad et al. In PODC 2019. Their simulation theorem allows us to run an R-round congest algorithm in roughly R over log n base delta rounds. But a weakness with their simulation theorem is that if delta is roughly linear, then this does not give us any speed up. But in our case, even if delta is in that range, if the algorithm allows us to sample a small set of nodes, that is alpha is small, our simulation theorem gives us a better speed up. Why are we even interested in simulation theorems? These simulation theorems allow us to connect complexities in classic models like PRAM or CONGEST to the complexities in MPC. It also makes it easier to port existing algorithms and also to design new algorithms for MPC. Let me talk a little bit about the assumptions that we make on the congest algorithms. We have to assume that the local state at each node stays bounded in size. And for the sampling, we assume that each node has an activity level, which is the sum of the sampling probabilities of all of its neighbors. And we assume that this activity level has to be bounded and not grow too fast. That is, it grows by a factor of at most alpha at each round, at each congest round. And this alpha is at least 2. We can apply our simulation theorem to get an algorithm for MIS that runs in log delta over square root log n rounds of the low memory MPC model. We use the algorithm of Ghafari, which we show that it fits into our sample and gather framework. This algorithm runs in O of log delta congest rounds, and we show that the activity levels are bounded by a factor of alpha equal to 2. And just a black box application of our simulation theorem gives the running time in the first bullet point. For two ruling sets, we can use our simulation theorems to get O of log delta raised to 1 over 6 round algorithm. This algorithm is done by using an algorithm called Sparsify, which is due to Bisht, Kottapalli, and Pemaraju, where in this algorithm, for a parameter f, we sample nodes with probability f log n over delta, and the neighbors of the sampled nodes are deactivated. Then we continue iteratively, where we increase the sampling probability in each iteration by a factor of f. This implies that we'll have at most log delta base f iterations, and since we sample nodes and deactivate the neighbors, these iterations are inherently sequential. So an example, these orange nodes get sampled in the first iteration, then their neighbors get deactivated, then in the next iteration more nodes are sampled, then their neighbors get deactivated, and then in the third iteration a few more nodes are sampled and their neighbors get deactivated. And we finish in this example, we finish in 3 iterations. The guarantees that are given by Sparsify are that the subgraph induced by the sampled nodes has a maximum degree of f log n. Notice that an MIS on the sampled nodes is a two ruling set on the entire graph, because a node is either sampled or it is the neighbor of a sampled node. We show that this algorithm fits into our sample and gather framework with alpha equals f. This is because the sampling probability does increase by a factor of f in each round, so the activity levels at each node will increase by a factor of f in each round. So for computing two ruling sets, we run Sparsify with our simulation theorem to get a set of sampled nodes in log delta base f over square root log n base f rounds, which simplifies to log delta over square root log n log f rounds. And then we run an MIS algorithm on the sampled subgraph using our simulation theorems again. And since the sampled subgraph has maximum degree f log n, the MIS algorithm runs in O tilde f log f over square root log n rounds. We get the required running time of log delta raised to 1 over 6. To this point, the results we discussed require a total memory of m plus n to the 1 plus epsilon. This can be superlinear in the input size for sparse graphs. And total memory is essentially the amount of memory used over all the machines. We generally want low memory MPC algorithms to use near linear total memory, which would be O tilde m plus n. A main challenge in coming up with near linear total memory algorithms is that we cannot use a single machine per node. This is what leads to the total memory usage of m plus n to the 1 plus epsilon in our simulation theorems, because we end up using one machine per vertex to gather balls around the vertex. So what happens is that we end up using machines with memory n to the epsilon for n vertices, and that leads to the n to the 1 plus epsilon term. And we want to avoid this, so we try to work in near linear total memory and adapt our simulation theorems to work in this regime. We require some additional assumptions that ensure that only high degree nodes are active. This allows us to charge the memory that is used by the simulation theorem to the input graph edges, and that allows us to show that the total memory usage is not too high. This allows us to get an R-round congest algorithm simulated in R over square root log delta base alpha rounds, whereas in the superlinear memory case, we had square root log n base alpha. We can apply our near linear total memory simulation theorem to recover the square root log delta running time of Ghaffari and Vito in the low memory MPC model. For ruling sets, we use our near linear total memory simulation theorems and show how to compute two ruling sets in log delta raised to 1 over 4 rounds, and more generally, beta ruling sets for beta greater than or equal to 2 in log delta raised to 1 over 2 beta rounds. Note that in the two total memory regimes, the exponents for beta ruling set are exponentially separated. So the question arises, is this inherent or is it an artifact of our techniques? Further open problems that I'd like to mention are, can we get a polylog n round beta ruling set algorithm for some constants beta and c? Second is, can we get deterministic versions of our sample and gather simulation theorems? Our simulation theorems are inherently randomized because they have this sampling step, and we need to use randomness to sample the vertices, but it might be interesting to see if we can de-randomize this process. More concretely, can we get a deterministic little o log n round MIS algorithm in the CONGEST model, in the MPC model? Thirdly, can we show a stronger and more general version of our sample and gather simulation theorem for the linear memory MPC model? This memory regime has been much more successful in getting exponential speedups using the graph doubling technique, but maybe our sample and gather ideas might give more speedups and more general speedups in this model. With that, I will thank you and hope you enjoyed the video.